Hey everybody, this is Harbin. Welcome to video notes 4.1. We're going to be doing these 4 things as our objectives for this PowerPoint. So, bulk properties of ionic nucleotide bonding. I'll explain why ionic bonds form, name and define and identify ions, and state what metals can form more than one ion. And here we go. All right, so read chapter 7, section 7.1 and 7.2. Okay, look at the pictures, take some notes, draw some examples. I think you should be able to answer the questions on 193 and 199. You might be happy. You might even say, wowzers yourself. Okay, so ionic bonding. It's a different kind of bond than we talked about in the last unit. Why does it happen? Well, there's electronegativity, and it's the ability to attract electrons when they're bonded. If an atom is very electronegative, it can actually pull the electrons all the way off of the other atom. And so that's what we call an ionic bond, when the electrons transfer from one atom to another because one atom is so much greater in electronegativity. So, who can do this? Well, it's not a who, it's an it. Non-metals can do this because non-metals are more electronegative than metals. And so the metals are losers. What do they lose? They lose their outer electrons, and non-metals gain outer electrons. So both of these were in the last chapter. Sharing, equal sharing, nonpolar, unequal sharing, polar. Here we go with ionic. One atom actually takes the electrons from the other, just like chlorine can take an electron from sodium, and then you can get a positive ion and a negative ion. Okay, so because ionic bonds form, and they form when ions are attracted to each other, they have high bond energies and a lot more properties. Okay, there's a full positive charge attracted to a full negative charge. They have high bonding energies. This is going to give them high melting points in general. Also, it's going to make hard, brittle materials. So ionic compounds are going to be solids at room temperature, and they're going to be hard and brittle. They're going to be electrical and thermal insulators. They are not going to conduct electricity when they're solid. Many of them dissolve in water, and then when they're dissolved in water, they do conduct electricity. They also conduct electricity when they're melted. And there's a metal and non-metal atoms bonded together to make these ionic compounds, and electrons are transferred. Okay, so what tests can we do to see if the substance is ionically bonded? Well, you can't touch this. Hammer time. You take a hammer and hit an ionic compound. Here's a structure, a model of what an ionic compound might look like. Okay, a model of what it looks like. So you have your positive ions and negative ions. But then you have your negative ions and positive ions. And so on in an alternating pattern. So if you bring the hammer down and see hammer, then you're going to put some ions that are negative next to other ions that are negative, and they'll crack. And that's why ionic compounds are weak. All right, what about this? If you take an ionic compound, oh look, it's a big old chunk of salt, and you put it into water, because water has a positive and negative side, it can attract the ions and pull them out of the crystal, and then water molecules can surround each ion. So ionic compounds can dissolve in water. Okay? Because when ionic compounds dissolve in water, then they have charges. The charges are free to move. Ionic compounds conduct electricity. So a lot of ionic compounds dissolve in water. A lot of ionic compounds, when they dissolve in water, and then when they dissolve, they conduct electricity. Right? Now you might be saying, wait a second, ionic compounds are going to conduct what? Well, they don't conduct when they're solid, but they dissolve in water and conduct when they're liquid or dissolve. Here's why. Look, when they're solid, stuck in place. Negative, positive, negative, positive, negative, negative, positive, stuck in place. Those charges can't move because they're stuck. But when they're dissolved, then they can move around and cause electric current to flow. All right, so why bond at all? So atoms make bonds to be more stable. And stability occurs when the valence shell is full, kind of like an noble gas. So if we got sodium with 1 outer electron and chlorine with 7 outer electrons, and chlorine is very electronegative, it will grab sodium's outer electron and fill its outer shell, and then sodium's inner shell is full, causing more stability. Okay, Let's talk about lithium and fluorine. Here's lithium. It's got 1 outer electron. Here's fluorine. It has 7 outer electrons. So if lithium transfers its outer electron to fluorine, then you get a lithium ion. Look, it's got a positive charge because it lost an electron. And the fluoride ion, it's got a negative charge, comes down an extra electron. And then the ionic bond is the force between the oppositely charged ions. So what do we even call these ions? Well, we can't just give them some random names. We got to have some rules for doing that. So make sure you know the rules. So cations are named the same as the element with the word ion after it. So if you see the name potassium ion, you should be thinking of potassium and then ion. Now I'll tell you how we get that positive in a second. When you see magnesium, you should be thinking Mg and then ion plus 2. I'll show you why. You know why, but I'll show you again. Those are cations, well, because they're positive. Anions are named like the element, but you change the name of the end of the word to IDE, the ending to IDE. You see chloride, you should be thinking Cl, and then -1. You see nitride, you should be thinking N for nitrogen, -2. I'll tell you how I got the charges in a second, but you already know. Okay, so here we go. What kind of elements form ionic bonds? Well, you got metals over here. Oh, look, there are all the green ones. And non-metals over here. So because they have big differences in electronegativity, then the outer electrons of the metals will transfer over to the non-metals. So you can use the periodic table to find out what the charges will be because you already know. Group 1 will make +1 ions. Group 2 will make +2. 3, here's going to be -1, -2, -3. All right. So, hey, sulfur. Well, sulfur is right about here on the periodic table. So what ion will it form? That's -2, and we'll call it sulfide. Lithium ion. Well, lithium is right about here. Lithium will make an Li plus, and we'll call it a lithium ion. Bromine. Well, bromine is right about here. Right? So it's going to be our -1 ion, and it'll be called bromide. It's negative, we change the ion. Positive, we say the word ion. Okay. Now, always metals. Some of the elements on the periodic table, when they form ions, will always make the same charge. And we're talking metals here. Okay, so non-metals never vary in charges, but metals can. So we're going to talk about the always metals. So you're going to be able to find the always metals because you'll always get a periodic table. In group 1, all these purple ones here will always form +1 charge. Okay, no doubt about it. Group 2 will always form +2 charge now. Then there are 3 more always metals: aluminum, zinc, and silver. Now, do you see how the word always begins with Al? Well, aluminum is Al, and aluminum is an always metal, and just remember this, always a +3 charge. Zinc's always a +2 charge, silver is always a +1. They make a little diagonal on the DT. Okay? So what this means is that anytime these elements form ions, they will form the ions with these charges. Lithium is a +1, potassium is a +1. So that's how I knew, hey, back here, I need lithium to be a +1. And then, even back here, when I was first doing it, I put +1 for potassium, +2 for magnesium, because they're always the same charge. Non-metals you don't have to worry about whether they're always or not, because they form the same charges. These are -1s, -2s, -3 for the non-metals. Okay, so what about the other metals? We're just talking about metals now for charges. If you know the always metals, group 1, group 2, and aluminum, zinc, and silver, then the other metals on the periodic table are ones that can vary their charges, meaning they might not have the same charge every time. So here's an example. Al aluminum. Hey, we just memorized that aluminum is an always metal. It always forms a +3 charge. Iron. Wait a second. Iron's not group 1, 2, aluminum, zinc, or silver, so it's not an always metal. It can be an iron +2 or an iron +3. So how are you going to know? Well, you're going to find out that there'll be Roman numerals and names to tell you which ion it's forming. And then if it's in a compound, you can figure it out. We'll practice that later. But for now, I want you to know that some metals always form the same charge. Group 1, group 2, and this line right here. But what if it's any of these other metals? Then it's not always. So you'll have to find a way. I'll teach you a way to figure that out. Okay. So monatomic ions is what we've been talking about, single atoms with a charge. You look at a periodic table. What about polyatomic ions? Well, poly means many, atomic means atoms, ions means charge. You've been memorizing them, okay? These are not the ones you memorized so far. But notice a polyatomic ion has many atoms, more than one atom, and a charge. Okay? Oh, here's the CP pi clone. He's not going to make that kind of pi, right? All right, so you need to know the formulas, the names, and the charge. So, uh, poly means many, atoms means, atomic means atoms, charge means ions have charge. So you need two or more atoms. So here's four things listed here. Which one of these is not like the other one? I see many atoms, I see a charge. I see many atoms, I see a charge. I see many atoms, I don't see a charge. I see one atom in a charge. Okay, so which ones are polyatomic? These are poly because they have many atoms and they have a charge. This is a covalent compound because it's two nonmetals. This is a monatomic ion, so there's one element with a charge. But there's some rules to help you know how to name them and memorize their formulas. So you memorized 5 already. Here are 2 of those. Chlorate, ClO3-1. Nitrate is NO3. So you're saying to yourself, I got those 2 because that's my clown's number. Excuse me. Now I have to tell you that if it ends in ATE, then there might be another ion just like it that ends in IgE. So there has to be something different. So we have a Cl, we have an O, and we have a 2. The charge is the same. So what's the diff? Okay, I wasn't talking about electronegativity there. All right, the difference is that if you look at the ite ion, chlorite, and you look at the 8 ion, the 8 has one more than the ite. One more what? One more oxygen. So I ate another oxygen, and that's why chlorate is ClO3 negative, chlorite is ClO2 negative, and there's Java the hydrogen chicken. So I want you to write what you think the formula is for nitrite and check it in class. Okay? Write that down. I'll put it on your open note quiz too if I remember. I'll remember. Okay. So, how do we tell the difference between elements, compounds, and ions? Elements have only one kind of atom in them. Right? Compounds have 2 or more types of atoms bonded together. Ions are atoms or groups of atoms with a charge. So here are some examples. All right, put these in your notes, and then we'll decide which one each is. For instance, if you see H2, is an element, a compound, or an ion? Well, there's no charge, so ions out. It's not two or more kinds of atoms because they're both hydrogen, so this is an element. That's one of our diatomic elements. Don't forget our diatomic. No, two, three, enough, Cobra. These are all the elements that when they hang out by themselves, they're never really by themselves. All right, so let's just look at one more. Okay, look, it's Fe plus 3. Well, Fe is one atom, so it can't be a compound. And then because of that, up there, it's got a charge as an ion. So you have to be able to tell the difference between all of them. So ionic compounds are compounds because they have 2 or more elements in them. But ionic compounds are special because they are going to either start with a metal or a polyatomic ion ammonium. Let's see, they're going to start with a metal or this ion, and then there'll be a non-metal with it or a polyatomic anion. Okay. So here are 6 things to look at. This is NaCl. How do you know if it's a metal and a non-metal? Well, you look at a PT. NA over here, CL over here. This is an ionic compound. Okay. Circle an ionic compound. Circle. Okay. This is a compound definitely because there's more than one kind of atom. This is a metal. This is nitrate, and that's why we're memorizing your polyatomic ions so that when you see them, you know them. So this is nitrate with a metal, so this must be an ionic compound. Okay. So looking at this one. This is sulfur and oxygen. If you look on the periodic table, okay, look at that periodic table. Sulfur and oxygen are both on this side. So this is a covalent compound because it's 2 nonmetals. 2 nonmetals. Right? So how is that different than this? This is ionic because it's a metal and a non-metal. Right? Look at this. That's all nonmetals. But wait, you're memorizing this polyatomic ion and that polyatomic ion. And so because it's got two different polyatomic ions in its ion, whoop, non-metal, over here on the PT, so it's covalent. And this is a non-metal and non-metal, but wait, it has a charge. So this is not a compound at all, it's a polyatomic. Don't be fooled again. It sounds like a Who song. Anyway, so, hey, look, it's the end of the PowerPoint. How do you know? Because you saw this slide already. And so now you can look at your textbook and see if anything in the textbook from Chapter 7 reminds you of what you just learned about. Okay? Made big hint. Wowzers, wouldn't that be good to put that in your notes? All right, finally, 1, 2, 3, 4 bullet points. Make sure you can describe the properties of ionic compounds. You can explain why ionic compounds form. You can identify and name polyatomic ions and monatomic ions. And you can tell which metals can form more than one ion versus which ones are always. All right, peace out. Have a great day.